So, even though the OSI model is a top down model, meaning when a sending computer sends a request to a receiving computer, the process starts at the application layer and travels downward through the other six layers. It's easiest to understand networking from the bottom up because the simpler devices are at the bottom of the OSI model. We're actually going to start in the reverse order. We'll start with layer 1 and discuss the physical layer. The physical layer is made up of our quote unquote dumb devices, meaning those devices don't know where data is going and they don't care. They don't direct traffic or errors, it's just simply physical connectivity to the network. When we talk about that, think about cable. Cable doesn't know where data is going, and cable doesn't know what type of data it is. Cable just provides a pathway conduit for the signal. Connectors like your RJ45 or BNC connectors just provide that connectivity to the network. I'll also mention hubs here because at one point in time, hubs weren't even powered. They were just racks that you plugged into, and that metal rack provided a pathway for signals to travel. So, hubs, even the ones we use today, powered hubs, just amplify the signal. There is no direction or error detection, just a pathway for signals to travel. As we go up the OSI model, we gain intelligence. The next layer up is layer 2, which is the data link layer. The data link layer is the only layer of the OSI model that has two sublayers, and those sublayers are made up of the first, which is LLC, and that stands for Logical Link Control. That layer is responsible for error detection. We won't say much about LLC that's not relevant to the Net Plus exam, but we do want to focus on is the second sublayer, which is the MAC sublayer. MAC stands for Media Access Control. So we have MAC addressing, and we also have media access, which is which system gets to communicate and when. With MAC addresses, the first thing we want to look at is the MAC address itself. A MAC address is a 48-bit address expressed in a hexadecimal. I have this circled for you here on our example on the left. In hexadecimal, separated by dashes or hyphens, we have a 48-bit address. The first 24 bits are specific to the manufacturer of the device. So if we all had 3COM network cards or something from the same manufacturer, it wouldn't be unheard of if the first 24 bits were the same for my MAC address as yours. Now, of course, manufacturers are given a wide range of addresses, but it wouldn't be impossible. The last 24 bits are unique to the host and unique to the network interface card. So even if we do have the same first 24 bits, our host address will be different. This is called the physical address or hardware address, but it's a MAC address. How it's referred to will really depend on the operating system. Ultimately, what we're talking about is the hardware address of the network card. The screenshot that I have here on the left was used by a command called ipconfig, which shows not just IP configuration, but also shows MAC address, and MAC addresses are very different from IP addresses, so definitely know that. ifconfig is a similar command that Unix uses, and folks that use Unix will use. So, ultimately, these show the MAC address. I do want to take one more minute to stress the importance of a MAC address. When traffic is on the network, an individual NIC, network interface controller, is going to examine the packet and look for its own MAC address. If the packet is destined for my MAC address, my network card pulls that off the network. If it's not, it leaves it here. So, what's critical for a host receiving data is the system's MAC address. What that also means is that as a sending host, I'm going to have to learn the client's MAC address. The way that happens is with a protocol called ARP, Address Resolution Protocol. What ARP does, it's broadcast based. So essentially, it sends out a broadcast that says, hey, is anybody 192.168.1.1? And that device will come back and say, oh, that's me. Here's my MAC address. And what you can see on the left is that I add the information to what we refer to as our ARP cache. Anytime you hear the term cache, cache is always a place where we store things that we think we're going to need again. So, once my computer learns the MAC address, the specific IP address, it'll store that in cache. So the next time we need to go to 192.168.11, I don't have to broadcast out. It's already there in my cache. Cache is very helpful. Later, we'll talk about some security issues that might be associated with cache, but cache also really does speed things up and make things quicker. Now, I'll also mention when we talk about media access control, who gets time on the cable. Quite honestly, we can't even say cable because there's wireless access, right? Via traffic across the airwaves. One of the main types of networking technology that we use today is called Ethernet. It follows an IEEE standard 802.3. If you want to remember that, Ethernet has three E's in it, so 802.3 is Ethernet. Ethernet uses a media access method called CSMACD. That stands for Carrier Sense Multiple Access with Collision Detection. That's a mouthful, right? Carrier Sense Multiple Access with Collision Detection, but it actually is exactly what it sounds like. If a network card has data to transmit, it senses the cable, carrier sense. The trick with that is the two systems could be sensing the cable at the exact same time. So, multiple access, they both throw their data out there. But if two hosts put their data on the cable at the same time, we have a collision. The network card is able to detect that collision, back off, and perform an algorithm to determine whether they can retransmit. So, CSMACD, Carrier Sense Multiple Access with Collision Detection. Expect collisions in an Ethernet environment. Another media access method that we don't see very much today is token passing. If you're familiar with the old token ring networks that were around in the 90s and early 2000s, basically there was a 24-bit control frame on the network. It would move from host to host to host. And if a system wanted to communicate, it would capture the token, then put its message out there. There was only one token, and you couldn't transmit without it, so we actually had no collisions in a token passing environment. That was one of its benefits. But Token Ring, which was the technology that used token passing, was proprietary. It was from IBM. It was expensive, it was difficult to work with, and we were bound to IPM as a vendor, so Ethernet really kind of won out there. There's also another media access method that wireless communication uses, and that's the 802.11. 802.11 is CSMA CA, Carrier Sense Multiple Access with Collision Avoidance. Essentially, what wireless systems do is it still senses whether or not anybody is communicating. Multiple systems can sense that at the same time, but instead of sending that data out, they send an intent message that essentially says, "Hey, I'm getting ready to send. Is that cool with everybody?" And if there are no other hosts coming back saying, "I'm sending too," then the wireless device transmits its information. So we don't have collisions in a token environment or in a wireless environment. We do in Ethernet, and one of our big challenges is going to be how we're going to address those collisions. This is just a quick summary of the different types of media access methods in the IEEE over to the left. I think it's a good summary to have. So remember, 802.3 is Ethernet. CSMACD, we expect collisions. 802.5 is token ring, token passing. There will be no collisions. One thing I'll mention, you can remember that token ring is 802.5 because there are 5 letters in token. Then we have wireless 802.11, no collisions here because we transmit our intent, and 802.12. I didn't mention this isn't something that I would anticipate using or seeing on the exam. I just have it here because this was used at one point in time. It's polling, where there's a specific server that polls network devices to determine if they want to communicate. That's not really an environment designed for speed or performance. It has really fallen by the wayside.